So the monkey hunter demonstration is a very famous, for some reason, couldn't tell you why, you can figure it out, I don't know, demonstration in physics. And it's very non-PC because it's a hunter hunting a monkey, which nobody wants anybody hunting monkeys. Nobody, well, okay, you can have your own opinion about hunting, but probably most of us might be a little bit shocked by that. But whatever, it's a traditional old example in physics, and every physics department does it, and most physics departments have a monkey. I actually, for our setup, it's Tony the Tiger, but which I know it's probably even worse. I don't know, just as bad to hunt tigers. In any case, the monkey hunter, we could change it in order to make it more PC, but it's we're doing it to stuffed monkeys and stuffed tigers, so I think we're okay. So let's go ahead and see the physics behind this demonstration that you saw from the MIT demo vault. We have the demo ourselves, but the MIT one is slightly larger, so it's a little bit more satisfying. So let's just set this up. I'm going to set it up. We're not going to finish it today. Let's just say we've got the hunter, which has a gun, and the gun is, let's just say it's at ground level. We're not going to worry about the delta y, the change in y that we get from the fact that the hunter is above the ground. Or we'll just say wherever the bullet leaves the gun is y equals 0. Okay. And let's say we've got a tree over here. Terrible tree, I know. I never claimed to be an artist. And let's say we've got the monkey, which is in the tree. Monkey. Okay, monkey. There you go. Monkey is hanging from the tree. And the hunter has aimed his gun directly, and yeah, good enough, directly at the monkey. And the point here is that if the monkey... If the moment the monkey says, I am smarter than the hunter, the moment the hunter shoots his projectile, I will drop out of the tree. Shoots his bullet, I will drop out of the tree. So the bullet's going to go over my head. And the hunter doesn't know what the monkey's thinking. So then the question is who is right? I think we already asked the question. We already showed the demo. So I think that you know that the bullet actually will still hit the monkey, and the idea being that that the bullet will not follow that straight line. That gravity pulls everything down, so the bullet actually goes off like projectile motion. At the same time, the monkey is falling down, and the bullet, as long as the gun is aimed directly at the monkey, the bullet will always hit the monkey, because both objects are undergoing projectile motion, even though they're different kinds of motion, right? One is falling straight down, one is has an initial velocity in the horizontal direction and the vertical direction. Both are falling. So if there was no gravity, what would happen when the monkey lets go? If there was no gravity, the monkey wouldn't go anywhere, and the bullet would follow a straight line, and it would hit the monkey. But there is gravity. So what happens? The monkey falls, and the bullet falls, and so they're still going to meet because they still fall at the same rate. Shouldn't be obvious, but we're going to prove that here. So this is the setup. So let's go ahead and give it some numbers. Let's say that the bullet starts, let's just say we're 100 meters. I'm just looking at my notes. 100 meters. Hold on a second. Say that this is 100 meters away, and the monkey is... I can't read my notes. Sorry. Blah. Okay, it took me a second to figure that out. Let's say the monkey is 100 meters horizontally away from the gun and 20 meters above the where the bullet comes out of the gun. And let's just figure out what happens. Okay, let's finish drawing our picture. I got to give you some more information. Let's just say that the initial velocity of the projectile coming out of the gun, the initial velocity, V0, is equal to, let's say, 50 meters per second, which is a lot slower than most guns, but the kinds of... well, it doesn't matter. It doesn't matter. It's just, let's just say it's whatever. It's a Nerf gun. I don't care what it is. 50 meters per second. Anything else I need to give you? Of course, the acceleration due to gravity is 9.8 meters per second squared in the downward direction. Initial velocity, okay, I think I've given you everything we need to know. So there's my picture. There's my beautiful picture with everything I need in it. First thing, let's just get it out of the way. Let's go ahead and take components of any quantity that needs components. That means we have to have axes. I sort of already set my axis, I guess. And I certainly probably made, I guess, that the plus x, the horizontal to the right plus x. And then should plus y be up or down? Gosh, I wish I had you guys here to tell me. Do you want plus y to be up or down? Let's go ahead and make plus y in the upward direction, since I think the last example I did, it was in the downward direction. And because it just doesn't matter. And now we can take components of any quantity, and we already have the components of displacement. It's 100 meters over and 20 meters up. Well, that's not actually, careful. I just said the components of the displacement. We don't know what the displacement of the bullet is going to be because the bullet doesn't go 20 meters up. It follows that projectile motion path. But we have the x and y separated. We've got the acceleration in the y direction, and then the only thing we have to actually take components of is the initial velocity. I'll do that in orange. The initial velocity has an x. Oops, this isn't orange. Whoa, that's some ugly color. Okay, so the initial velocity has an x component, v0x, and a y component, v0y, in booger green. So we have to take those components. And I drew v0. V0 should be along the straight dotted line. I sort of drew it above that just to separate it out. But what's the angle here? Right, there's an angle that we need, this angle theta, in order to get v0x and v0y. Well, remember, v0 is along that dotted line that makes the triangle up, and the triangle, so I'm just going to redraw, let's go ahead and highlight this triangle right here. This triangle right here, the big green right triangle, has a side along the bottom, which is not 20, which is 100 meters, and a side up on the right, which is 20 meters. And so we actually know what this angle is here. That angle is given by the displacement, or by the distances. It's not the displacement, I keep saying that, but the bullet, nothing is going to displace 20 meters up because the bullet falls. But that angle is given by the dimensions given in the problem, and that's the same angle that we use to take the components for the initial velocity. It's the same angle. So therefore, the tangent of theta is equal to 20 over 100, 20 meters over 100 meters. And so that's the angle that we're going to use for the velocity triangle as well as the dimensions of the problem. So therefore, theta is equal to 11.3 degrees, because I can do that in my head that fast. So therefore, we can look at the right triangle making up the initial velocity, and we can see that v0x must equal 50 meters per second times the cosine of 11.3 degrees, and v0y is equal to 50 meters per second times the sine of 11.3 degrees, and v0x is equal to 49 meters per second, and v0y is 9.8 meters per second. That is just a coincidence. Didn't mean to make v0y have the same number as the acceleration due to gravity, but whatever. Got to deal with it. So then we can actually look and see that v0y is in the positive direction, v0x is in the positive direction. Look at your triangle. So those quantities are positive when we write down. Let's go ahead and write down what we know and what we don't know. Actually, the next step is to write down the equations and then what we know and what we don't know. So let's go ahead and just say projectile motion, delta x equals v0xt, delta y equals 1/2 at squared plus v0yt, ay t squared, vy equals v0y plus at, a sub yt, vy squared equals v0y squared plus 2ay delta y, and then figure out what we know and what we don't know. So we have set up this problem, And next time I will finish solving it. Poor monkey doesn't know what's going to hit him.